We're now going to talk about directional derivatives. So let f be a function of x and y. And let u be a unit vector. Let's say it has components a and b. And unit here means that the length of this vector is 1. And the length, of course, is the square root of a squared plus b squared. And then we define the directional derivative of f in the direction u at a point, say, xy, by the equation duf of xy. Well, let's write it this way. It's going to be the derivative at t equals 0 of f of x plus at, comma, y plus bt. So what this means geometrically is here's the xy plane. Here's the point xy. And let's say u looks like this. So what we're doing is we're adding t times u to the point xy. So there's a line through this point whose tangent direction is u. And we're evaluating the function at different points on this line and taking the derivative. So in other words, we're just taking the derivative of the function as we move along this line through the point xy in the direction u at unit speed. Now, by the chain rule, if f is differentiable, so of course this definition assumes that this derivative is defined. Now by the chain rule, if f is differentiable, then it will be defined. And furthermore, what do we get? So we get duf of xy equals df dx at xy times d dt of x plus at at t equals 0 plus partial f partial y at xy times d dt of y plus bt at t equals 0. Now, of course, the derivative of x plus at is just a, and the derivative of y plus bt is just b. So I can simplify this whole expression by just saying that duf equals a partial f partial x plus b partial f partial y. So for example, if I take the directional derivative with respect to the vector 1, 0, so here a is equal to 1 and b is equal to 0, so I just get partial f partial x. And if I take the directional derivative in the direction 0, 1, well, here a is equal to 0 and b is equal to 1, so I get partial f partial y. So as we know, the partial derivatives with respect to x and y measure the rate at which f changes as you move in the x direction or the y direction. But the more general directional derivatives allow you to measure the rate at which f changes as you move in any direction, although by this formula you just get linear combinations of the partial derivatives with respect to x and y. Now for functions of 3 variables, it's very much analogous. So if f is a function of x, y, z, and u equals abc is a unit vector, then we define duf at xyz is the derivative at t equals 0 of f of x plus at, comma, y plus bt, comma, z plus ct. And if f is differentiable, then you can use the chain rule to write this as follows. So if f is differentiable, then duf is a partial f partial x plus b partial f partial y plus c partial f partial z. And again, you can get the partial derivatives with respect to x, y, or z by taking the directional derivative when u is one of the coordinate vectors. Okay. Now there's a convenient way to package all of the directional derivatives using what's called the gradient vector. So if f is a function of two variables, we define the gradient of f at xy to be the following. So some people write this as grad f at xy. In this course, we're going to write it as an upside down triangle. So gradient of f at xy, and this is actually a vector. So maybe I should put a little arrow on top of this upside down triangle, but I'm not going to do that. Anyway, it's the vector consisting of the two partial derivatives. So the gradient, at every point, the gradient is a vector, assuming, of course, that the partial derivatives are defined. Otherwise, the gradient is not defined. And if f is a function of three variables, then the gradient of f at xyz is the vector consisting of the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, all evaluated at x, y, and z, assuming that these derivatives are defined. Now the relation between directional derivatives and gradient is as follows. So if u is a unit vector, and f is differentiable, then the directional derivative in the direction u of f is equal to u dot product with the gradient of f. This is true in any number of variables. So let's look at this in three variables. Okay, so let's say that u is the vector abc. Then we know that the directional derivative in the direction u of f is equal to afx plus bfy plus cfz. But the gradient is the vector fx, fy, fz. So we see that this vector in the middle is the dot product of these two vectors above and below it. So this formula will be very useful later when we talk about some of the theoretical properties of directional derivatives. So again, this gradient is a vector which is a function of x, y, and z, so it depends at what point you are. So for example, if I have a function of two variables, say f of xy equals xy cubed plus sine of xy, sine of x plus y, then what's the gradient? So the gradient, so first we have the partial derivative with respect to x, which is y cubed plus sine of x plus y. And then we have the partial derivative with respect to y, which is 3xy squared plus sine of x plus y again. Okay, sorry, this is a angle bracket. All right, so this is a vector. It's a vector depending on the point xy. And if you want to calculate the directional derivative of f in any direction, then all you have to do is take the dot product of the direction vector u with this gradient vector.